Hi and welcome. Today we are presenting our student proposed project on a modular entertainment light fixture. My name is Alicia Oliva.
I'm Jade Holberger.
I'm Gabe Odachowski.
And I'm Amy Ariel. Automated lights originated in the 1980s, and the development was originally restricted to the two founding companies. Since then, many more companies have entered the market, and lights can be seen everywhere, from concerts to churches, live events, and trade shows. There are three main components to the light: the head, yoke, and base. These allow the light to pan and tilt, which provide the light's two axes of motion. Despite having just two axes of motion, moving lights are notoriously complicated. As a result, tours and rental houses carry fully operational spares at all times. This requires a lot more truck space, which in turn also uses a lot more CO2 emissions and other wasteful resources.
After identifying these problems, our team devised a solution to create a modular light fixture design that would separate the head, yoke, and base components. This would reduce overall environmental impact, as tours would have less spare parts that they would need to carry, since they can replace an individual module on site. This then reduces the CO2 emissions, since there would be less truck space needed. In addition, this would improve worker safety by making it easier and faster to repair on site, reduce overall production costs, and promote future compatibility and production of economies in scale. We looked at the Fortnite World Cup, a large-scale tour that you can see in the picture here. And after some calculation, we were able to derive that we could save up to a metric ton of CO2 emissions for each tour stop. The touring industry consists of thousands of tours all happening at once. So imagine how much of CO2 emissions we could save if the entertainment industry implemented a modular lighting design for all of their shows.
Originally, we had 12 to 15 designs, a few of which you can see in the sketches on the left of this page. Eventually, we narrowed it down to 3 and ultimately decided on the dovetail design based on how closely it met our design criteria. In the center 2 pictures, you can see this version 1 of the dovetail, which had a trapezoidal shape. We decided against this shape due to the fact that it would have a high stress concentration on the corners, as well as how difficult it would be to fabricate. Finally, we moved to our version 1.5 design, which incorporated a square dovetail. And each of the pieces in this dovetail are able to separate from one another. On this design, we incorporated several safety mechanisms, the first being the push button lock and this other being a safety latch bar. This helps with safety during install and also keeps the joints securely attached. It also includes a limit switch, which you can see on the far right bottom, which allows the light to be reset to a home location and rotate from that point so it knows where it is in space.
As Alicia previously discussed, the joint was developed in 2 CAD versions that we called version 1 and version 1.5. From these, version 1.5, seen here in the upper left, was tested and modified through 2 rapid prototype versions made on 3D printers in the VCU makers studios. Then the final joint assembly was constructed from aluminum, steel, and polycarbonate in the VCU maker garage. The full construction of the light's frame components, including the yoke and base, were designed in 1 CAD version, which was then machined to fit the existing lights. Initially, in the joint, high current blade style Molex connectors were the core of our design. However, those products had limited availability due to COVID, which required them to be substituted for lower pin count, but equally mechanically and electrically robust D-sub style connectors designed for high DC currents drawn by the motors and the head units. We had to design our light joint around these products. For precise motion and holding position, the drive system needed to move cleanly without jerking or bouncing and hold precise positions when at rest. For this motion, the joints are driven by trapezoidal profile belts and pulleys, powered by stepper motors with encoders for position feedback, which is a common solution to this problem in industry. Likewise, the framing of the light body is typically made of bent sheet steel, but this is a difficult manufacturing process and creates a heavy final project. For our project, the framing of the drive system was made from aluminum for its effective combination of strength and low weight, while the rest of the structure of the yoke and the base was made from polycarbonate sheets fixed between aluminum standoffs to save as much weight as possible. This brings us to our final design. The complete prototype shown here is a full-size model of a stage light with the separable joint included, demonstrating the ability to easily switch between head units in the field. It pans 540 degrees about its vertical axis and rotates 270 degrees about its horizontal axis. These are standard ranges of motion in the entertainment industry. All three joints are the same design. This aids in end user servicing as well as faster manufacturing and achieves our ease of use repair goals. The components of the safety interlocks previously mentioned are already proven in other industries, and while their integration together is novel, the additional safety offered by their use is critical to worker safety in end-use scenarios. The light itself weighs less than 20 pounds, depending on the installed head unit, which is less than half of our original weight specified. However, due to the size of the joint, the total volume envelope of the light is larger than was originally intended. The base of the moving light fixture includes space to use existing standards for power and data interfaces so that it can be adapted to be used in modern venues with other manufacturers' products. This also allows our light system design to be made easily compatible with future designs produced by larger hardware manufacturers in the industry.
Here's an overview of the control systems for our modular light. It is separated into intermodule communication between the modules themselves on the light fixture and external communications between the fixture and lighting control consoles. External communication is handled by a WebSocket-based API, and translation layers take protocols such as DMX, ArtNet, and SSEN and translates them into the WebSocket API. Because we're using an API, we are able to add more translation layers for future protocols that might not even exist yet. For intermodule communication, when an upper module, such as the head or yoke, comes online, it sends a message to the base advertising its existence. The base then requests information about the upper module, and the upper module replies with its associated parameters and values. The base at this point is able to create a fixture profile for the entire fixture and make that available to the lighting designer and lighting console for use. When the lighting designer wants to set the value of a parameter, the lighting console will send that information to the base. The base will translate that information and then send it to the associated upper module. That upper module gets that value and then updates its respective output. When the lighting designer wants to change that, the same thing happens. The lighting console sends that data to the base, it translates, and then the upper module responds.
To prove potential for a modular head, the team retrofitted 2 LED lights donated by community members. Each light uses an adapter block to attach to the dovetail and so it fits snugly into the yoke. In the future, manufacturers may design their own heads as they please, so long as they meet the physical and electrical requirements of our yoke and base design and incorporate a dovetail light component to fit into the yoke's receiving saddle. The full fabrication, funded by the Sternheimer grant, allowed us a lot more learning experience than a regular 3D printed prototype. Some things we would work into a production-ready version include designing a separate joint for the yoke base connection instead of using the same joint at all 3 contact points. A separate design would allow us to more specifically address the needs of each connection joint. Secondly, add DMX input to the base. Although designed to be in place, the 2 were ultimately cut due to time constraints.
Thank you to everyone who came out to see us at the VCU Engineering Capstone Expo. On the right, you can see the web GUI that's powered by the microcontroller in the base with live status of the light. Once Gabe removes the head, the software recognizes that a module is missing and updates the parameter list accordingly to remove those modules. Once he snaps the head back into place and engages all the locking mechanisms, the software recognizes that a new module has been attached and adds the parameters back into the software. Once the light is enabled again, it runs a quick motor calibration to make sure that it is aware of where it is in space. Unfortunately, we were only able to get one of the 2 desired axes of motion working by the Capstone Expo. However, given that they have similar implementation in hardware and software, getting both operational would be a simple task with one already working. We were honored to receive first place for excellence in design for multidisciplinary teams from the College of Engineering. We would like to give a special thanks to our faculty advisors, Dr. Bradley Nichols and Dr. Alan Dosif, as well as Greta Daughtry and the Richmond Ballet, who donated the lighting fixtures we used as heads in our project.
If you have any additional questions or want to talk further, please reach out by sending us an email or connecting on LinkedIn.